we could understand, particularly in this case, the audio modality, non-speech audio, how we could use that, what the building blocks were. Let's think a little bit about the present. Now this video has got absolutely nothing to do with my research. It's always nice to start with a funny video.
Hey, just that, thanks.
Are you sure?
Yeah. Username? Nick Ann?
No.
And 1983?
No.
Zami Pops? Sorry. Zami Pops?
No, okay, don't worry, I'll help. What's your postcode?
Oh, it's GU749ZT.
Welcome back, Nick, forever.
Oh, great.
Please listen carefully to the spread license agreement before continuing with your question to the local grade. If you do not, blah, blah, blah. You also agree not to use any bread-based product for any purposes prohibited by United Kingdom law, including without limitation, design, development, and manufacture of missiles, chemical, nuclear, or biological weapons. Tick. I'm afraid you've timed out.
What? Sorry. Hello?
Excuse me.
Oh, yeah, howdy.
Just what, Nick, sir?
Yeah, we just...
What's your username?
It's Nick Forever, but number 4, not the...
Gotcha.
Yeah.
Okay, I'm just going to check that you're a real person. Could you say that for me? Okay, how about this one?
You know what, forget it.
Which one?
Potter Mice.
You're in.
Great, I'm in.
£8.85.
It's supposed to be £98.
That's express delivery.
What's that?
Oh, well, it's express delivery. It's fast. So there's standard. Standard delivery. That's £4.99.
Why?
Bread insurance. You didn't untick the don't decline bread insurance option.
No, I think I'll risk it.
It is quite close to the sell-by date.
Don't care.
98 pence it is. If you want to pop back in 5 business days, it'll be ready for your collection.
Well, I need it now, obviously.
Oh, okay. You want the take-home today price? So that's £3.27.
You know what, I'm going to go.
Come back soon.
So that's nothing to do with the work. It's the present. That's what like happens now if you took a bad shopping model and applied it to a real setting. So what we're really going to talk about, we're really going to talk about haptics. So we talked about sense of hearing, and now we're going to talk about sense of touch. So haptics, 2 parts. So it's all to do with the sense of touch, but there's 2 parts to the sense of touch. There's the kind of kinesthetic part, kinesthesia, which is kind of motor activity, movement, kind of forces, and then there's cutaneous touch, which is stuff that comes through the skin, like temperature or vibration. There's a handy model of that provided by ISO with their breakdown of the structure of haptics. So we have haptics at the top, confusingly named touch on that side, which is really cutaneous, kinesthetic stuff on this side, and then the different bits of your touch sense which fall down each of those paths. So actually, touch is really complex. You might call it one sense, but actually there's multiple things going on there. So oftentimes, psychologists call it somatosensory because there's a kind of whole bigger thing going on. So we're going to talk about cutaneous first, which is thinking about this kind of left-hand side. And we'll think a little bit first about tactile feedback. This is the kind of default option when it comes to haptics. So these are vibrations that you're going to perceive through your skin. So pretty familiar, if you've got your phone in your hand and the phone vibrates, or you're playing a game and the controller vibrates. That's the kind of thing we're talking about. Sensed through the skin by these things called mechanoreceptors. All sorts of different ones of these all over your skin. Some of them detect stronger forces or weaker forces pressing against you. Some are detecting static touch or dynamic touch, all sorts of things. There are different depths, different densities across your body. That's a little slice through some skin, so you can see all these different things. The ones for the lighter touches are closer to the surface, the deeper touch ones are further down. So distributed across your body in different locations. And also a large part of your brain and your motor part of your brain is dedicated to tactile perception. So there's a little slice through the brain there. It's a little bit hard to see in the picture, but these are all different parts of your body and the sensing and the motor control for each one of those mapped to the to the size. And this is this weird guy mapped to the size of the amount of that stuff that is in your brain. There's an even more disturbing picture of it. So you can see that his hands, for example, there's a huge amount of your brain dedicated to dealing with hands, huge amount dedicated to dealing with lips and tongue. But arms, not a lot goes on with these, so they're very spindly, because not a lot of brain is associated to that. But a huge amount of your brain, motor cortex, is dedicated to dealing with hands. So isn't it a shame that all we do with our devices is just stab at them with our fingers? There's a lot more that my brain can deal with than just stabbing at the bottom of the finger. There's an important thing to think about as a problem here that we don't have with audio. And this is to do with fidelity. So there are very many ways to stimulate those mechanical receptors, and we'll talk a few of them as we go along. Vibration motor in the phone, very cheap, easy to use, but they're not very good. They're not very good in terms of matching how good your perceptual system is. If you think about audio, for example, if I had a great sound system out in the corridor and I had a symphony orchestra, maybe we could play both of them and you wouldn't be able to tell whether it was a real symphony orchestra or a recording, because the sound quality is really good. Unfortunately, haptic hardware is nowhere near as good as our skin is perceiving it. You know, with our skin we can detect things which are 1 millimetre or less apart on the fingertip. We've got 4 millisecond temporal resolution. We can detect things with different time differences of 4 milliseconds. But building devices that can match our capabilities as humans is very difficult. We'll come back to that in a minute. So, how to use the vibratactile feedback. We talked a bit about that with audio and how to use it. How about this? So, of course, there's the boring things like ringtones of gate vibrations. It's a bit like the background music that we were talking about with audio. But there's other things you can do. There's other advantages. Of course, it's eyes-free, so I can feel a vibration from my phone in my pocket without having to see it. It's quite handy. I know I can receive a notification. So my visual attention could be elsewhere. Works well in a noisy environment, so no matter how noisy it is, I can still feel the vibration of my phone. That's quite good. It's very personal. So the problem we talked about with audio, unless you're wearing more fancy Bose sunglasses, is that if someone's phone rings, everybody in the room can hear it. But if someone gets a message and the phone vibrates, nobody knows, except for the receiver. Disadvantages, so the fidelity, is much lower than audio. That's the problem, is that it's hard to make a vibration device which can match the capabilities of me as a human. And that means it's quite hard to generate realistic haptic experiences using a vibration device. What does a vibration motor in your phone feel like? Kind of like a fuzzy sensation. It's not really like anything I touch normally in the real world. The other downside is I must be in physical contact with it. So if my phone's on the table over there, then I'm not going to feel haptics. So it doesn't have that transmission over distance that audio has. So you see there's advantages and disadvantages of this compared to audio. So one of the first things that we did when we started working on haptics was took all the stuff that we knew from audio and then just piled it into haptics. If you think about it, a kind of vibration, well, it's the same as a sound really. It's just a frequency changing over time. So we created these things called tactons, which are tactile icons, and they're pretty much the equivalent of the Earcons I talked about before, the ones where you can build up complex messages on small units. So this time you can create messages by varying things like the tempo, the rhythm, the waveform, the location on the body. So you have a similar set of parameters to the ones you had with audio. And in many ways the skin is not far off the ears in terms of the perception of some of these things. Rhythm, for example, the perception of rhythm through your skin is pretty much as good as perception of rhythm through your ears. Waveform is much worse because you can perceive a lot through your skin, but not such a wide variety of waveforms as actuator in the right place. So that would be like the spatial audio. I've got plenty of body location to use. Here's some examples of different body locations that we tried. So we put lots of different vibration motors around mobile phone prototypes, so you could use different locations on your hand. We had them on a belt, so you could have them around your waist. We used that for navigation. There was several wrapped around in a watch strap, so you could have them on your wrist. So some locations are much better than others. As I mentioned before, the distribution of the haptic sensors across your body isn't uniform. And even if it is, there's some other problems that come up. So good locations were things like the forearm, the waist, and the hand. Hand, not surprising, we saw that huge amount of my brain capacity that was dedicated to hands. Yeah, easy to get good performance from 4 locations across the hand. People can easily identify 4 different locations. Things like wrist and ankle were a bit less effective, especially when you were walking. The trouble with things like wrists and ankles is they're very bony. If you put the vibration motor on a bone, then it tends to vibrate along the bone, so it's very hard to localise. But if you put it on a kind of flabby central part, the flab stops the vibration spreading, so it's much easier to localise where it comes from. So you have different kinds of issues to the audio issues. One of the kind of default experiments that we did was looking at tactile feedback on the touchscreen for button pushing. In the old days, when you touched the buttons on your phone, you didn't get any tactile feedback. If you use an iPhone, you still mostly don't, but a lot of Android phones do. So we wanted to see, well, how could we improve typing performance? Typing performance on phones with physical buttons is much better than touchscreen. That's an example of a really old PAL device. Of course, you don't get those anymore now. So what we wanted to do is say, well, could we get back to the kind of high text input rate you got from a physical button device by using kind of artificial vibrations from the vibration motor on our phone? So we compared the performance of real buttons, those, to touchscreen, and then to touchscreen with added tactile feedback. We did it in the lab. We also did it in the Glasgow subway. If any of you know the Glasgow subway, it's very noisy, shakes around a lot, it's full of vibration. So it's a really good testing platform, and happens to be 5 minutes from my office door. So we tested all these different types of interfaces with people entering text. So the physical buttons were the best, but the touchscreen plus the tactile buttons were pretty much as close to that and as good. You could get pretty good performance, almost to the level of the physical buttons, by using tactile feedback. Without tactile feedback, touchscreen alone was really poor. So, yes.
What exactly was the tactile feedback?
So what we tried to do was we modelled the type of button pushing, the type of feedback you got when you were pushing buttons. So it's not actually the same feedback as you would get on a mobile phone right now. We went to a whole lot more trouble to model the kind of feedback that you got. The push down, a little bit of bounce, and a bit of release. So we tried to model that really closely because we were using better quality motors than in the phones at the time.
Getting that feedback on a touchscreen or a custom interface?
There's a custom interface. So what it showed was if you did good tactile feedback, it made a performance benefit. If you didn't do good tactile feedback, it didn't have any benefit. But if you did good tactile feedback, you could get performance which is as close, almost up to the level of those physical buttons, which is pretty good. We did tactile feedback like that, tactile feedback like that for a long time, but then eventually I kind of got a bit bored of that. So we tried to think about what other aspects of touch do you have that we could use. Remember, the multimodal interaction, we want to use all that stuff that you've got as a human and see if we could use it for interaction. So, what about thermal feedback? So we go back to our model again. So we're still in the cutaneous side, but looking at temperature perception. So temperature mostly is unused when you're using a device. Maybe you've touched your phone and it's really hot and you think, maybe something's bad, I better restart it. But most of the time it's not used at all. But yet, for humans, in bare skin contact, it's always present. Every time I touch something, I get some thermal feedback. I can tell the different materials partly because of the temperatures. monitors. I can't say, 25 degrees, but I'm really good at detecting changes. So what we thought was, well, can we use it for communication? Can I encode information in the same way as we talked about for vibrotactile, for example? There's some other potentially interesting properties as well. Because thermal feedback has quite a strong emotional response. We'll come and talk about that in a minute. But there's, maybe warm things feel nice or hot things feel bad. As I mentioned before, it's a kind of key technique for determining the material properties. You might say, well, is this made of metal or is it kind of shiny silver plastic? You touch it and it's quite cold. Yeah, okay, so that's probably metal then. So maybe things I can't tell visually, I could get from touching it and detecting temperature. There's also things like children's hotter and colder game, where you might tell them where their presents are hidden by telling them they're getting hotter and colder. So there's the sorts of things built into language about that. Potentially, you could use that as an alternative to a vibration motor. Maybe you could do that, maybe you could do other things. So I mentioned this before, but vibration motors don't really give you a convincing feeling of touching any material. I can't simulate the feel of my shirt with a vibration motor. The quality of those actuators is just not good enough. So their ability to produce stimuli is much less than my perceptual capabilities. And fixing that, well, it's certainly not a computer science challenge, that's more of an electrical or a mechanical engineering challenge, and that's really difficult. Apple spent millions of dollars making the haptic engine for their devices. One thing then you could try and shortcut that, let's try something different. If it's very difficult to do vibration, maybe thermal device is easier. If I use a thermal device, then I can stimulate my skin with that thermal device in exactly the same way as if I was touching a warm thing in real life or a hot cup of coffee. So therefore the feeling is much more realistic. It's much easier to stimulate my thermal system in a way that matches the real world than it is with the vibration. So hey, let's try and see what we can do with thermal. We can maybe do something more interesting there. Technology is pretty straightforward actually. We use these things called Peltier heat pumps. So they are a kind of standard electrical component. You can plug it into two wires. For me, if you can plug it into an Arduino, then I'm happy. So this, you can plug it into an Arduino. So if I'm using this kind of dielectric material, one side cools down, the other side heats up. I don't really understand how the magic happens in the middle, but this dielectric effect causes one side to warm up, one side to cool down. And they're very easy to use. So we built our own one. Doesn't look pretty. These are the Peltier elements here. They're about that kind of size. You can get them all different sizes. It runs on batteries, communicates via Bluetooth, so I can connect it to different things. So then we did a whole load of different studies about how we might use it. So, for example, what are the most sensitive body locations? How much change do you need in order to be able to detect that something's happened? Of course, the interesting thing about thermal feedback is you don't want to get too hot, otherwise it could hurt. So you have to be careful. So you have to put, well, what's the minimum amount of change that we need to be identified? How fast should it change? We looked at static versus mobile use. Does being in motion affect the way you perceive it? Of course, we talked about clothes versus bare skin. So currently, my phone is in my pocket. So there isn't bare skin contact between any thermal device and my skin. So how does it work through different types of materials? We also looked at varying indoor and outdoor environments. How does your perception of temperature change as the environmental temperature changes? So we did all sorts of different studies looking at how that worked. Here's an example of a couple of participants wandering around the department with one of our early devices, and where we're looking at mobile use and how thermal feedback changed during mobile use. So we came up with a whole load of design recommendations from all those studies. So actually, your palm is most sensitive, more sensitive than your fingertips actually. Palm is good, which is quite handy if you're holding a device, because it's likely to be touching against your palm. Wrist and arm are also good, so wrist may be good if you have a wearable with a device in it, or your arm if you have something like on your arm up there. So stimulus intensity should be minimum of 3 degrees. So you only have to change by about 3 degrees, and people could easily notice. If we changed 1 degree, sometimes people didn't notice, especially when they were mobile. 3 degrees, easy to detect. 6 degrees was about the maximum that we used. We normally start about 30, because 30 is the kind of neutral temperature for your skin. So we got to 30, 38, not getting anywhere near anything painful, and we go down by the same, not getting anywhere near anything painful. So both the warm and the cool stimuli were detectable, but interestingly in our first experiment anyway, the cool ones were preferred. We of course thought, well, people will like the nice warm ones, but actually people preferred the cool ones. The cool ones were also detected the fastest. Now bear in mind that we're only using a temperature range of 26 to 38 max. Temperature, when it's hot temperature, is detected very quickly, and in fire and out of fire very fast. We don't go near those kind of temperatures because it would burn people, and the ethics committee would probably not give us the chance to do that anyway, or they shouldn't. So we do a much more compressed temperature range, which is maybe why that is true. Moderate rate of change, we need to change about 2 to 3 degrees per second, gives you good saliency, people can tell things are happening, they can notice the changes. But you might actually need to use a lower rate of change for higher intensity stimuli. So the thing that we found was, we changed by 6 degrees. 30 degrees to 36 degrees, that's nothing. Go on holiday, 36 degrees, that's nice. But the fact that we changed quite quickly, people thought, no, it's going to burn me. If it keeps changing at that rate, it's going to burn me. And of course it didn't, only change 6 degrees. The interesting thing was, it's very easy to trigger a kind of an affective response. It's going to burn. So we have to be careful. Something about temperature, if it goes up very high, it's going to cause you damage. Therefore, you want to get away from that. So we even found that by changing 6 degrees, which is a very small amount. So that was looking at some of the kind of basic parameters, same as the kind of we did with audio, looking at how we use those audio parameters. Then we thought, well, okay, what about applications? So one of the things that really got me interested was this idea of affective or emotional responses to thermal feedback. And even if you think about it, that's kind of embedded in language, because you might say, he's a warm and loving person, or he's cold and distant. So there's all those words are kind of embedded right in language, with emotional kind of connotations. So we think, well, can we use those to create affective feedback? Maybe I want to create an emotional connection between me and the device, me and a character in a game, or me and a product, or something like that. Could we use that? So we use this model, Russell's model of emotion. Not sure if you've come across this before. It comes from psychology. It has these 2 axes. One is called valence, one is called arousal. So valence is the kind of pleasantness, going from kind of unpleasant things to pleasant things. And arousal is kind of the amount of it. So not very much to a lot. So you can see that Russell then mapped lots of different emotions around this model here. So you might be miserable, you've got low valence, but not a lot of arousal. But if you increase the arousal, you might get to angry or afraid. Or if you get more positive valence and increase your arousal, you might get to happy. Or you might get relaxed if it's positive, but not a lot of activation. So you kind of map those emotions around the space. Nice Windows start of the icon. So what we did then was look, well, can we map some thermal cues into this space to see if you give people thermal feedback, how do they respond emotionally? We also did that with vibrotactile cues and thermal cues on their own. And actually, on their own, they weren't that good. We didn't really get good coverage of that space. We ended up just kind of getting small coverage kind of in the middle of it. So then what we did was we tried to expand it in a more multimodal way. So for this one, we used thermal feedback, vibrotactile feedback, some audio feedback, non-speech audio feedback, and some visual. In this case, visual was kind of like not high resolution visual displays, kind of pulsing lights. So we combined them all together to try and create a big palette of emotional cues. So what you can see on this picture here is the same model as before. You can see the same words as before, but all these crosses and dots and things with the different cues that we created. So you can see that now we have cues which cover a whole lot of this emotional space. So we found, for example, in this case, warmth, people felt generally positive towards that, so it increased the valence. Cool's a bit more negative, decreased the valence. Larger or faster changes were more negative. Smaller and slower changes were more positive, calm and relaxed. So what you can see from this is that we've got all those dots and crosses across that space. Now it means if I want to, say, create an emotional icon, I can say, right, I want to have one which is astonished. So I could use ones which are like that. Or I want something which is a bit kind of gloomy. So I could use one like that. And underneath that, there's some combination of a thermal cue, a vibrotactile, and audio and visual. So I could combine those. So if I then wanted to create a message, which I could send to you and say, I've just been fired, then I might say a kind of gloomy message, or I'm delighted. I might be able to use one of those. So it gives you a kind of palette of emotional cues to choose from. The interesting thing was, only worked when it was multimodal. When we tried the individual modalities, it was less successful. We didn't cover the whole space. What might you do with that? Well, our initial motivation was kind of richer emoji that I could send, rather than sending a smiley face, I could send a much richer message, which the person receiving it would then get a richer meaning from. Then we also used it for things like enhancing the emotional richness of images and music. So, to try to enhance an image, you could either then give an emotional cue to match what was in the image, or kind of like a bit further, or you could reduce the effect of the image by giving an emotional cue which was a kind of lower version of that. Also looking at games and characters, so we created a chatbot, and we then looked at how you might use those kind of more friendly type emotional cues from the chatbot versus the more negative cues, to see if we could help people build a relationship to the chatbot better. You can also imagine that in physical products, you want to touch a product and you want to experience, have a good experience of that product. We've also thought about in cars, so for example autonomous vehicles, giving you some feedback about their state. And if the car is happy, you're happy. If the car is feeling nervous, then you should maybe start feeling nervous. Maybe one of the sensors is broken or something like that. So you can use these in all sorts of different kinds of situations. So continuous haptics, that's the stuff that's perceived through the skin. Vibrotactile devices, very common, very cheap, but it's not very good resolution. They just don't really match what you can do as a human. Therefore, all the experiences you create with them are kind of a bit artificial and not very engaging. We did make tactons with those to create messages that we could deliver in the same way as Earcons, and that worked very well, because therefore you're not trying to create the feeling of something, you're just trying to give a message. But to try and avoid that problem of the hardware just not matching to my human capabilities, we switched to thermal feedback, where the hardware matches my capabilities perfectly. And then we used to create a whole range of different things. I just showed you these emotional ones, but we also created a whole range of other different types of cues there as well. So thermal feedback works really nicely. And again, an untapped part of my human capabilities. Let's take a quick look down the other side of the graph. This time kinesthetic haptics. So here we're looking at the things which involve movements, forces, things like that. They're sensed by sensors in my limbs to get the position, and then muscles to monitor the forces, so I know how hard I'm pushing. So if we look at our good old graph again, this time we'll be going down the right hand side. And the first one we'll talk about here is pressure. So pressure input, or more formally, would be isometric force input. Again, little studied in HCI. You can squeeze your device as much as you like. Most of the time it doesn't pay any attention. but commonly used in other things like musical instruments. Digital keyboards, musical instrument keyboards have used pressure input for a long time. So humans are extremely good at using controlling pressure. Again, think of that, the massive hands in my weird model. A lot of my brain is dedicated to that. So using pressure input is a very good thing, a very easy thing for a human. So then, humans can do it. I want to use it in my interactions. So can we use it as another input mechanism? Potentially, I could use it by pushing on my phone screen. I wouldn't have to do any X and Y positioning. I could kind of do Z positioning by pushing into my device. I wouldn't have to necessarily have to move my finger around. I could maybe do something eyes-free, using this kind of Z axis into my phone. Maybe it doesn't require any kind of change of grip. If I'm trying to interact on a large phone, reaching that top stuff oftentimes means I have to change my grip to get to the top, to the bottom. But maybe I wouldn't have to do that. I could just push into the screen and do things on the screen. But there's very little work out there. So if you think about holding your phone, I've got 5 good input points, and actually maybe a few more, because my index finger can move around a bit. I can tap on the back, on the top, or on the side, depending on the size of my phone. Hardware, again, pretty standard. This thing here is a force sensing resistor. It's basically a plastic film that you can stick on different things. You can connect it to an Arduino, so I'm happy. But they're very cheap, they're very flexible, they're very thin. In real life, well, they come in different sizes, but in real life it's more like that size. So easy to use, easy to add to things. So the first experiment that we did was pressure input on the keyboard. This is a single input. Something pretty simple was what we created a pressure-based keyboard which allowed you to change case by pressing harder or softer. Press hard, you get an uppercase letter, soft, you get an uppercase letter. And we gave you a kind of pressure meter, you'll see it in the video, a pressure meter at the side that goes up and down as you press. I'll show you the video of it. So you can see, as you press on the screen, you get the pressure meter pops up, and the harder you press, you get a big A, and the soft press, a little A. Pretty straightforward. People were really good at doing that. The nice thing is, you don't have to swap between as many keys. If you think about normally pressing an uppercase letter, I have to go press the caps key, press the A, press the caps key, turn it off again, press the B. With this, I have fewer presses to make. And every time I make one of those presses, I have a chance of, press the wrong one, missed. So I have fewer button presses to make, therefore it increases performance. So it works really nicely when you're mobile, because it reduces the number of button presses, and therefore the number of errors. So single finger pressing, that works well. The next thing we thought was, well, okay, if I'm holding my phone, I'm grasping it, I've got all these contact points around the edge. Can I use grip or grasp as a way to control the device? And then we thought, well, one of our motivations I mentioned at the beginning was that I might be carrying stuff and I haven't got 2 hands free. Could I take something which is a 2-handed interaction, me clicking on the screen, and make it into a 1-handed interaction just by me holding the device and squeezing it in different ways? So our motivation was to try and free up one hand so I didn't need to use that for the device. So we built ourselves a phone case covered in pressure sensors. We looked at where people touched it and put the pressure sensor in the right place. And then what we did was we calibrated all the different grips you could have to find out which are the best grips to make input. I'll show you a little video of it in action. So that's the device. It doesn't look very pretty, but it was functional. And we'll move along a little bit. screen. This shows all the things that work. Then we do, to test the performance of all the different grips, we did this thing called a pressure-based linear targeting task. If any of you are familiar with Fitts law, this is basically doing Fitts law with pressure. You choose different targets, you measure targets different sizes, and you can kind of calibrate the performance of the different grips and different input styles. And then we'll just go right toward the end. You can see a bit of it at the end, maybe. Maybe that there. So here you can see what we finally used it for was map zooming and scrolling. So you can zoom in by squeezing, releasing, and then rotating the map by pushing it on different pressure sensors on the different sides. And the nice thing you can do is you can zoom and scroll at the same time, just in the same way you could do with your fingers. You can do the same thing with the phone. You can squeeze and then squeeze in different directions. So we compared the standard way of doing it, 2 fingers on the screen versus our squeezing one. And our one-handed one was equal to or better than the traditional one in all situations. So people could use squeezing really reliably for input. Nice thing was, there's no finger occlusions. This big fat finger problem where you have 2 big fat fingers on the screen, well, they weren't on the screen anymore. So it didn't get in the way of looking at the map. Worked well when walking. So one problem you have when you're walking is I have to couple this hand to the screen reliably, and because there's 2 separate things, that's kind of hard to do. Whereas if I'm holding and squeezing it, I've got a much tighter grip of it in my hand. Therefore, it's much more stable. Therefore, input is actually much better when you're walking. So squeezing the device worked really nicely. So single finger was good, squeezing was good. What next? Well, I have 2. So maybe I can use 2 hands. So our motivation in this case was like this. So maybe I'm using a tablet. And I've got one hand, if I'm right-handed, I've got one hand doing most of the work. Left hand is really playing a supporting role in this case. Maybe the left hand could do a little bit something more interesting than just holding the device still. Maybe the left hand could do some pressure input. Not do too much. Certainly can't move the left hand around very much because I might drop the tablet. So it's got to have a stable grip. But maybe I could do some pressure input with that. Our motivation here is this area of bimanual interaction. So there's a thing called the kinematic chain theory from Yves Guillard. And the kinematic chain says that for a left-hander, or for a right-hander, let's say, you would frame the interaction with your non-dominant hand, left hand, and you'd use your dominant hand to do the details. So if you think about writing, the left hand gets a bit of paper in the right place, the right hand does the details. So you combine them together, they have different roles. If you're right-handed, the left hand doesn't do the details. And if you're doing framing with the right hand, then you're kind of wasting its capability. So in our case, the non-dominant hand was supporting the device. So it can't move, but it could do pressure input. It could do something general to frame the whole interaction. But it can't do the details. A, you've dropped the device, and B, it isn't really capable of that. And with the dominant hand, then doing the interaction. So we ran a series of studies to look at this. So what we wanted to find out was, can users do the pressure input with their non-dominant hand without having a negative effect on the dominant hand? So what you don't want to do is then make the left hand really great, but the performance of the right hand is really rubbish. What I want to do is get both of them to be good. So we looked at 2 broad tasks. One was targeting. So how accurately can the left hand do a targeting task combined with the right hand doing a targeting task? And we looked at kind of maintaining. So in this case, the left hand has to hold a particular value, particular pressure value, but the right hand does the work, does the details. So it could be, for example, choosing a colour and then drawing that colour, or choosing a line thickness and drawing that line thickness. I'll show you a video. You can see the pressure menu on the side. side. You can see the pressure sensor, gaffer tape to the top of the screen. So what I had to do in this one is I had to choose a particular pressure menu item. We just marked them out as colours. And then my right hand had to do a typical kind of targeting task. So I had to do something with this hand, something with this hand. Collar, flick, collar, flick. Then the maintaining one, in this case, I then had to hold the pressure at a particular value and then do multiple clicks to see how well I could maintain this one at the same value. How much did it deviate? You get the idea? So as it turns out, there was a low impact on the dominant hand accuracy. So what I was doing with my left hand did not make my right hand worse. I was still able to do fine target selection. So we measured target selections, how far away they were from the centre of that target, the time taken to click on the targets. So they were still able to do precise interactions with their dominant hand. Pressure accuracy was good across all the conditions, so they were able to use their non-dominant hand well to be able to choose those pressure menu items, either to choose the one they wanted or to maintain the pressure. So the pressure didn't interfere with the dominant hand. People were able to accurately select pressure targets by both applying and releasing. In the previous literature, most people had looked at pressing to choose a target. Sometimes you may be pressing and then releasing, and then pressing again, releasing. So we looked at more dynamic kind of pressure selections. People were pretty good at that. We also tested more complex dominant hand interactions as well. So what do I mean by that? So in that case, we were just tapping on individual items. We also then moved on to looking at the typical two-handed rotations, pinch and zoom, translations. So people were still able to do those ones accurately whilst applying pressure. So pressure worked really well in that scenario. So non-dominant hand pressure didn't interfere with the dominant hand action. So then you kind of get a free extra channel of input. The hand that couldn't do anything normally because it's just holding the device is now free to actually do something and contribute. So you kind of increase the amount of information that you can give to the system. Here is an example of one of the things that we did. No? No? So this is using the pressure input with a dial in this case. So the dial allows you to move across this section of albums, and pressure then zooms you in to either albums, or artist albums and tracks. So you see, it's a slightly weird aspect ratio. This was a project done with Bang & Olufsen, the Danish hi-fi people, and they had a screen that they were trying to sell at the time, which was like a kind of wide or long letterbox kind of shape, so it was like that, which doesn't fit so well on a monitor like this. But they didn't allow us to show that because it was commercially sensitive. They never went on to solve it. I'll play down this video. So this is Danny, the student who's working on that. So you can see he controls that very fluidly with his right hand, who then sets the scene. Am I looking at artists, albums, or tracks? And then moves between them by using the other hand. So they did put a version of this into one of their products anyway. Right, so a little bit of summary. Finished a bit earlier this time, wasn't I? See, it's not very hard to tell whether it's an hour or not. So, been thinking about kinesthetic perception in this second part. So this is the perception through the muscles and joints. This is more for like physical interactions. The first half was skin-based ones, so vibrations and temperature which come through the skin. This one is now, I'm starting to exert some force. Gesture would also come under this kind of category. I didn't really talk about gesture interaction, but gestures would also come under this kind of category. So this is physical interaction. So pressure turns out to be a really rich way to communicate. Now maybe that's not surprising, given the fact that humans are really good at pressure in everyday life. You know, I can pick up an ice cube without dropping it, and that becomes super subtle control of pressure. Or if you think about playing musical instruments, the pressure of the bow on the string marks out the virtuoso performer and the person who's kind of scraping across. Or if you think about drawing, the kind of fine control of the force of the pencil on the paper changes line thickness and things like that. So humans are good at it. We've got lots of evidence of from everyday life, but our devices don't really pay attention. So pressure is a rich human skill. We also saw how much of the brain is dedicated to it. So it works well for individual fingers. So just pushing on that keyboard, for example, worked really well. People were able to easily change between upper and lowercase. We did another version of that where you could move between layers of keyboards. So we had numbers, we had different kind of emojis as well. So you could move between different layers to make it easier to get those different layers. Grip works very well. So we looked at that 5-point grip around the device. So people can use that grip to make rich input. In our case, that freed up then one hand from that two-handed interaction. People could then squeeze one way or the other to rotate. They could squeeze to zoom in and out. So grip worked really well as an input technique. Then bimanual interaction. So we looked at that hand which is doing nothing right now, the kind of supporting hand, and see how we could use that. By using this kinematic chain theory, gives you some guidance about, well, what should you expect the non-dominant hand to do? You can't do too much, because it can only set the scene. You can't do the details. So setting the scene in our case was just applying a single parameter of a single value of pressure, which you could then map to something useful in the interface. And that didn't have an effect on what my dominant hand was doing. Dominant hand was still able to make fast and reliable selections. So that's the end of this one. So fine, that's not too bad, is it? Oh, Aaron, yes, you're going to.
Are you like to mention anything about where this is showing up at the moment? I don't want to steal your thunder, but I have a very nice example of where your work has gone straight into product.
Oh, right, give me that, yes.
But so the Google have a Pixel phone, and on that device they have a thing called the Active Edge. And this year at UbiConf they explained the engineering process that they went through to create the Active Edge. At this year's Chi conference, which you were the general chair for, they had a paper all about the theoretical underpinnings of where the Active Edge research came from into a product. And the third paper that's listed under there is this work.
Oh.
So it's now in product, so it's a great story of impact going from theoretical gluing sensors or gluing actuators or gluing little touch points onto devices into real product. But I guess it goes to Miguel's question, will this continue, or do you see a great shiny future for...
Well, do you want to I'm not sure what to say. Do you want a bad example?
Yes.
So, from, let's say, the iPhone 6 to the iPhone XS, they had pressure input. Any iPhone users in the audience? Anybody use the pressure input that they had on there? You push hard on the screen. Yeah. Do you use it? You're like, you don't use it. So if you're not familiar with it, you can press on icons, for example, and it will bring up menus or things like that. iPhone 11, gone. Took it out. One of the reasons, I think, is because they didn't make any use of it. The pressure sensing wasn't fantastic, it was okay. They didn't use it for anything. Well, they could have had an uppercase keyboard. They did all the technology they did for an uppercase, lowercase keyboard. They didn't use it for anything. So I think that's an example of where they spent, let's say, $1 billion on the hardware, interface. And now they've just gone on. Now you just have to press a button for some time, and then the same menu pops up. So I guess Google take it, and then Apple give it away. So I think Apple's case is exactly that they didn't really think about how to use it in user interface. And so they kind of wasted an opportunity.
So where is the best opportunity that you see now for this?
There's another phone, which I saw a demo of the other day, which has got squeezing around the edge as well. I forgot what brand it is. But they also done something with squeezing around the edge. I think squeezing around the edge has got a lot of possibilities because you've got lots of rich input there. But I think for simple input in a lot of situations, pressure is quite good because I don't have to find the target very precisely when I do that, I can just push. So in eyes busy situations, a simple input works really well. Yeah.
Do you see some of these sort of less conventional inputs having use of things like VR?
I mean, the VR case is a nice one because I can't see the controller. I'm never going to see the controller. So something that makes it easy to give you a more kind of analog kind of input. You can certainly do something like that, yeah. You're gripping that controller with lots of great contact points. Rather than having to find the different button to push to do something, maybe gripping and squeezing will give you a way to go.
So, have you done any work with how this sort of interaction works with older people? Because specifically on 2 points, one would be they don't have great, like my grandma has arthritis and can't squeeze things very well. And then the other one is they're not as computer literate as our generation, for example.
Yes, so I think that being able to squeeze at different forces is important. So what we did was kind of calibrated the forced space of the people we tested so that you knew what the minimum maximum range was. So a massive guy with huge hands can't necessarily apply such subtle forces and can apply much more force than maybe your grand could do. So calibration of the pressure space was definitely the right thing to do. Inadvertently in one of our experiments, we set the maximum pressure too high. And people couldn't get to the last menu item because they couldn't squeeze it hard enough. So you have to get that right. And probably there's a bit of personalisation you want in order to be able to get the pressure zone right. Some people might have a much wider one, some people might have a much narrower one, depending on their physical capabilities. But I think, is it a natural interaction technique? Well, I'd say probably yeah, because squeezing things in the everyday world is a very normal thing to do. You know, I go to the supermarket and pick up an orange and squeeze it to see whether it's good. You know, so it's a very normal thing to do. Using it in interface in the appropriate way, as maybe the Apple example shows, is potentially tricky. Maybe Google will do it better. But I think it's a very human kind of interaction to have. So I don't think that's a problem if you design it right.
Did you do precision comparisons to when the tablet was being supported to when someone was standing up holding it? Because I can imagine if you're trying to find a target on the screen as you're trying to at the same time counterbalance that, it could be difficult.
Yeah, we didn't do so. So our use case was bang Olsen. That is sitting on your sofa, controlling your media system. So that was our use case in that PhD project. So we didn't do much freestanding and holding. Freestanding and holding would be different because also sometimes you kind of wrap your hand around the tablet and might even be interacting on the other side of it. So that's an interesting situation. And no, we didn't. I still think you could probably design a good pressure interaction to go with that, but that's not one that we tried because of the usage scenario we were given.
So for your keyboard with the capital letters, does that slow down typing because you sort of spend more time focusing on pressure? Because if you're typed very quickly, there's quite a lot of variation in pressure intensity.
Yeah, so it all comes down to error rate because every time I have to move to another key and I miss it and do something wrong, then that slows the correction and slows me down. So if you don't switch case very often, then it isn't going to help you at all. If you switch case a lot, then it has advantages because there's no chance of missing the shift key or the key to bring up the emoticons or the key for whatever else. So, especially in mobile settings, it improved typing performance for the people we tested. Yeah. So but you could set some kind of gating pressure threshold under which it doesn't do anything, or you might have to say, I need 2 contact points in these 2 places before I start doing anything. So you can probably cut off a lot of those accidental ones by a bit of interface design.
Are there not some engineering concerns present with some of the results raised by the temperature feedback systems? They were raising that some of the most responsive areas for that were the hand and the wrist, where you're competing with smartphones and smartwatches for space on the user's body, and obviously those both have those resources.
Yeah. So I mean, I guess our motivation was that you could incorporate it into a smartphone or a smartwatch rather than having it as a separate device. So then you could build it into the back of the device and it would warm or cool you as go. Now the thermal feedback is further away from product than the pressure one. So people often complain that the thermal one consumes more power. It doesn't consume enormous amounts of power because you only have to change by a small amount for people to notice, but it does consume power. Also, when you cool one side, the other side heats up. And heat is always something that you're trying to get rid of in those kind of designs because there's always heat problems. So it does bring up other issues. So my motivation for all of these things is, well, I'm not a mechanical engineer or electrical engineer. My job is to say, is it worth spending $1 billion and some clever mechanical and electrical engineers to make it work? I'll show if it's even worth it. If it isn't worth it, because you can't do anything useful with it, then don't waste that resource. If it looks like it's plausible and it could do something, then Samsung could come along and say, great, we're going to put that in the Galaxy S25, and they spend some years then building it. So they aren't kind of setting the ground as to whether it's worth it or not. I can't solve those kind of issues because I'm not the right kind of engineer for that. Right, you first.
Yeah, following up with the temperature one, so you were showing how you could use it for mapping emotional space and everything. How would you, for example, just moving up and down the y-axis instead, which is just the rate of change, what's the solution for going up and down there when there isn't actually much temperature change, it's more about how quickly it changes?
So you say you want to go more up and down on the kind of arousal
Yes.
axis. Well, I mean, one thing you can do is combine more senses. So adding other senses in allows you to do more richer things. You know, with filming, you haven't actually got very many things you can change. You've got plus or minus and the rate of change and the extent. That's it. You can't do anything else. Whereas with haptics, you've got a bit more, with audio, you've got a bit more. So you could enrich it by using some of those other modalities as well. When we tried to do, we were quite excited about, yes, we've looked at that graph with tactile feedback and went, really rubbish. We just got a small amount of the space covered. Thermal would be that thing, so emotional, it would be great. And then we just got a small, different bit of the space covered. So we thought, what are we going to do? And then we tried to combine more modalities, and actually, multimodality is the way to go because they all do different things. So by combining them all, then we managed to cover more of the space. So that would be my answer.
Do you know whether pressure would be advantageous over just using kind of a little analog slider? Because in a lot of circumstances, it seems to have the same kind of range of control, but it's far less obvious that it has this affinity that you can actually interact in that way.
So just maybe moving it would be an interesting comparison to make. The advantage of the pressure one is that potentially you could combine it with the slider, so that you could have slide with light touch, slide with medium touch, slide with hard touch. Could give you 2 parameters.
That's me. I think the affective work is really interesting, but I wonder to what extent it's stable. So could you talk a little bit about whether this varies a lot per person? So for a person, something warm and vibrating might mean something, and for a different person might mean a different thing, and even for the same person in different circumstances, like if I'm just coming from the street, I'm looking for warmth, I feel a little bit different than if I'm in Cuba and I don't want more heat in my body, etc.
So we didn't find that much difference between people. People were broadly in agreement about the feeling of those, so there wasn't a huge amount of variability. An interesting question is variability between you in a cold place and you in a warm place. So we tried to investigate that. So what we did was, we did the same experiment from January to July. We got the same set of people to come back once a month, and we got a set of new people set at the same time. They sat outside the department, they did some thermal-based interactions, and then they went away again. So we did it from January all to July, because we had no way of controlling the temperature in any other way. We haven't got a temperature control lab or anything. So part of the answer was it didn't really change it that much. So one thing that you might do, of course, would also be to adapt your base temperature. So you could look at skin temperature and say, okay, skin temperature is currently 35, therefore we can start that as our base, rather than mostly just saying skin temperature is normally about 30. Let's just go up and down from 30. The question is, would you like then cooler feedback when you're in a hotter place? We haven't completely seen any evidence of that, but it's hard to test in Glasgow. If you find somebody send me to a hot place, I'll happily test that for you.
Okay, we should probably stop for lunch now. So, thanks for a very thought-provoking lecture.
Thank you.